Washington State University. Go Cougs!
Hello and welcome back to the course on Statistical Inference. We're in Module 2 where we're covering several different classification methods. And in this fifth part, we'll be looking at ensemble methods, which is a way of taking several different individual classifiers and combining them into a more powerful one. So in an ensemble method, as I mentioned, the goal is to learn a set of classifiers or an ensemble. And then these classifiers will each attempt to classify the example data and will each make a prediction. And then those predictions essentially comprise a vote, and the majority vote will win. There are other ways of combining these predictions, but that's the standard approach. Now there's two different kinds or main ways of doing ensemble methods. The first is called boosting. And the idea behind boosting is that we're learning a sequence of classifiers. And in the sequence of classifiers, each classifier is biased toward correcting the errors made by previous classifiers. And this is usually accomplished by weighting each of the examples. And so as the different classifiers are learned, the examples that on which mistakes are made, their weights are increased. Examples that it is getting right, their weights are decreased. So as we progress, the classifiers get more and more specialized towards trying to predict the harder examples. And then, of course, once it's complete, the sequence of classifiers is, each one of them is used for a new piece of data. Each one of them makes a prediction, and then those predictions are combined, usually as a majority vote, to come up with the final prediction of the ensemble. The scikit-learn package has one of the more popular techniques for doing boosting called AdaBoost. And AdaBoost handles the weighting of the examples, but the underlying classifier is kind of up to you. You can use decision trees, neural networks as the base classifier that is modified based on the change in the weights on the data that's input to it. The other main way of constructing an ensemble is to use bagging. The idea behind bagging is that you are modifying the input data set, but you're doing it by randomly sampling from the original data set. So for example, if I had 100 examples, I could generate, say, 10 different subsamples by randomly sampling from that 100 with replacement. So I would still get 10 different data sets, each with 100 examples in them, but some of those examples will be duplicated. And so that introduces a random element, and so the classifiers that are learned from those 10 different data sets will be slightly different, and hopefully they won't all make the same mistakes, and the performance of the ensemble will be better than the performance of any one of the individual classifiers. Now again, there are several different approaches to bagging, and a lot of them are based on the choice for the underlying classifier. But one of the more powerful methods is called the random forest. And the idea here is that the underlying classifier that's learned is the decision tree. So again, you generate multiple data sets that are all slightly different, and you learn a decision tree for each one, and then you vote the results or combine them in some other method. So one form of randomness in the random forest is the different randomly selected data sets. But an added randomness that's injected into this process is that, as you remember in decision trees, at each point in the tree at a node, we have to decide on what feature to choose to split for the decision tree. And normally we would just choose the feature that has the highest value for the metric we're using. We were looking at the Gini impurity metric. But in a random forest, typically what's done is of the features that are available to choose from, it randomly chooses a subset of those. And then within that random subset, it will rank them based on the metric that you're using. So that introduces another form of randomness into the process. Again, the idea is to produce multiple trees that generally make the same predictions, but hopefully don't all make the same errors. And if that's the case, then the ensemble will have better performance than any one of the individual classifiers, or in this case, decision trees. Okay, so let's take a look at the code for doing the ensemble method. Again, it's not a whole lot different from what we've seen. You should have this ensemble Python code available in the course materials, and we do the normal thing of importing the ensemble module along with our read data functions and our accuracy metric. Now we're going to be using the random forest ensemble, and one of the main parameters for the random forest is how many different trees to learn. And the default is actually 10, and that's what we have here. But this is one of the main parameters you will want to change to try to tune the method to get the best performance. Next, as usual, we'll read in our data, and again, we're just working with the 3 acceleration values to be consistent with the other implementations we've been working with. But normally you would want to input all of the sensor values in which to learn your trees. So here's the actual learning part. So again, the name of our classifier is the random forest classifier, and we pass in the parameter setting for the number of trees we want to learn. We then fit that classifier to our training data. We then use that learn classifier to predict the training data and compare that to the correct values in order to produce our final accuracy of the classifier. So let's take a look at that in action. Move over to our terminal window. And again, I'm in the source directory with all of the different classifier methods, and of course the one we're interested in is the ensemble method. So let's run that. So we see we get an accuracy of about 96%. You might have noticed from the slide, though, that the accuracy can vary, and that's because there is a random component to this classifier. So if we actually run it a few more times, we may see some different values come out. So here it actually got perfect accuracy on the data set. A little bit in between. So there's a few runs. Again, the difference mainly being that random component both in selecting the data set for each classifier and in selecting the features at the nodes of each of the decision trees. So jumping back to the notes. So again, you'll see a range of accuracy values come out based on the randomness, but as you can see, this is one of the first classifiers to get 100% performance on the training data, and in general is performing very well. So that completes our coverage of the different classification methods for doing statistical inference. So to review, we've looked at the nearest neighbors, the naive Bayes, decision trees, neural networks, and just now the ensemble methods for doing classification. Also along the way, we saw some of the pre-processing techniques, namely for scaling the data so that all the different dimensions have about the same variance. Of course, we were using the evaluation metric of accuracy to measure the performance of our classifiers. And we saw a variety of ways of visualizing the results. Matplotlib mainly being used to visualize the decision surfaces or regions or boundaries for our classifier. And then we saw how GraphViz could actually visualize the decision trees that we're learning as part of the decision tree classification method. So that completes Module 2, our coverage of the different classification methods for doing statistical inference. Congratulations. So now you should have quite a toolkit for analyzing data, specifically any sort of behavioral analysis on sensor data. These tools should be sufficient for you to learn classifiers in order to do accurate prediction.